We now look at how to test the convergence of series. By the necessary condition for convergent series stated in item 1, if we can show that the limit of the sequence formed by the terms of a series does not equal 0, then the series diverges. In the example, to find the limit of the sequence formed by the terms of the series, we divide the numerator and the denominator by I. Then we can see that the limit equals 1, which does not equal 0. Consequently, the given series diverges. In item 2, the comparison test roughly says that for a pair of series with non-negative terms, if the larger series converges, so is the smaller series. Likewise, if the smaller series diverges, so is the larger series. We illustrate the limit comparison test with an example. To use the limit comparison test, we choose a series with known convergence such that the limit needed by the test is a finite positive number. The convergence of the given series can be determined using the series with known convergence. The fact in item 3 says that, for a given series, if the series formed by the absolute values of the terms of the given series converges, so is the given series. In this case, we say that the given series converges absolutely. In the example, we use a known convergent series and the comparison test to show that the series formed by the absolute values of the given series converges. Therefore, the given series converges absolutely. The fact in item 4 shows a relation between series and improper integrals. It enables us to use many techniques developed for improper integrals to test the convergence of series. In the example, the convergence of P series follows from the known convergence of P integrals. A fact about the convergence of alternating series is stated in item 5. In the example, upon verifying the two conditions, we conclude that the given alternating series converges. The ratio test in item 6 says that if the sequence formed by the absolute values of the ratios of consecutive terms converges to a number, then we can use this number to determine if the given series converges. We'll work on an example question. In this question, the limit needed for the ratio test equals 0, which is less than 1. By the ratio test, the series converges. Note that, as a byproduct, the limit of the sequence formed by the terms of the given series equals 0 by the necessary condition for convergent series. This limit may not be too obvious. We'll work on an example question. In this question, the limit needed for the ratio test equals 0 for any value of x. Since the limit is less than 1, by the ratio test, the series converges for all x. In this case, we say that the interval of convergence is the set of all the real numbers. We'll work on an example question. In this question, the limit needed for the ratio test equals the absolute value of x. By the ratio test, the series converges if the absolute value of x is less than 1 and diverges if the absolute value of x is greater than 1. There remain only the cases that x equals 1 or -1 when the series evidently diverges. Therefore, the given series converges if and only if x is strictly between -1 and 1. So the interval of convergence is the open interval from -1 to 1. We'll work on an example question. In this question, the limit needed for the ratio test equals x squared. By the ratio test, the series converges if x squared is less than 1 and diverges if x squared is greater than 1. There remain only the cases that x equals 1 or -1 when the series converges, since they satisfy the two conditions under which an alternating series converges. Therefore, the given series converges if and only if x is between -1 and 1 inclusive. So the interval of convergence is the closed interval from -1 to 1. The root test stated in item 7 requires evaluating the limit of the sequence formed by the ith root of the absolute values of the nth term of the given series. If the limit exists, we can use it to determine whether the given series converges. We'll work on an example question. In this question, the limit needed for the root test equals 3 over 5, which is less than 1. By the root test, the series converges,